Hello everyone, and welcome to the Magic of Materials presentation. Materials engineering covers pretty much everything that you encounter throughout your daily lives. It contains metals, polymers and plastics, ceramics and glasses, and pretty much everything in between. Every day you are coming into contact with the various kinds of materials. But materials engineering isn't just about the things that we can already do, it's also about improving in every way possible. For mechanical design, we are working on 3D printed metal jet engine parts that are going to begin testing this year. We're working on polymer solar cells to capture energy that was previously missed. We are working on creating concrete that produces less CO2 emissions and is stronger and more durable. And in computing, we're developing liquid metal thermal paste and a whole range of new electronic materials to make your computers and phones even better and faster and make their batteries last longer. For our first demonstration, we have the polymer ball drop. So if you'll watch the video on the right, you'll see that one ball bounces while the other hits the ground and basically stays there. And this is because polymers can come in a lot of different forms. In the ball that bounces, we've added components to space the chains out and allow them to flex and come back, creating an elastic response so the ball bounces. In the not bouncy ball, we've added a component to make it dense with material that can absorb the impact. Polymers are great at having a lot of variety without needing to change very much at all. The main chains are the same. All that we change is what we added onto them. For our next demonstration, we have shrinky dinks. Now you may have seen these before, they've been around forever, but do you understand the science behind why they work? So those polymer chains that we talk about, some of them love to curl up in a tight spring shape when they're cold, and then they'll stretch out when they get warm. To make the shrinky dink sheets, what we do is we heat them up so those chains stretch out, and then we freeze them, locking them into place without even giving them a chance to curl together. When we reheat them, the chains are going to stretch out again, but they're going to cool slowly, cooling up and creating the shrinking effect that makes it a shrinky dink. We can use these even for nanoscale materials to create excellent patterns. Our next demonstration is determining polymer strength. So if you look at the video on the left, we're pulling this polymer, stretching those chains out, and it's creating lots of crazy colors. Those colors correspond to different areas where the chains are being pulled harder than others. And the colors will change as different amounts of light can move through them. We use a polarizing filter so we're able to see this even when we wouldn't be able to normally. We can use this to help make our models of materials even better. For our next demonstration, we have metallic glass, the atomic trampoline. So in the tube on the left, the ball is just bouncing into a regular plate of steel. In the tube on the right, it's hitting a trampoline of metallic glass. Metals usually form crystals, which can shift and move around when there's an impact. Metallic glass doesn't have this pattern, so it doesn't deform on the surface, and all that energy goes back into the ball. We make metallic glass by taking molten metal and freezing it super fast, 100 times faster than we do most metals. It's a little bit like the difference between building with large Lego bricks or a whole bunch of small pieces. If you dropped two parts that were the same size, you would pretty much expect where it could break when you're using large pieces. But on the small pieces, there's no telling which piece would break first. NASA is using metallic glass to make super good gearboxes that can withstand the cold of outer space. For our next demo, we have shape memory metal. So we can take a piece of metal, stretch it out, damaging it, but when we put this special piece of metal in front of our heat gun, it gets back to its original shape. So How that works is we use a nickel titanium alloy. This has great elastic properties and it has a shape memory material. And this is due to the unique nature of the crystals inside of it. If you can sort of imagine holding a stack of paper, you can bend it one way and then the other, but it always goes back to the same shape. The nitinol is similar. We shift the crystals one direction, we add heat to shift them a new direction, and as they cool down, they go back to our original position. This gives it some really neat properties. We are going to send tires made out of this material into space because they don't require air and they can take a ton of damage. And we can also use them in medical devices, allowing us to move inside veins where we can expand or contract depending on what needs to happen safely without invasive surgery. These material innovations can make life a lot easier. Thank you for watching our quick presentation about materials engineering and the various things that we can do with them. There are tons of opportunities out there for materials engineers to get involved in making the world a better place and improving pretty much everything that we interact with on a daily basis. I wanted to especially thank Material Advantage and the University of Kentucky for hosting E-Day and for helping get all these videos set up and all the places where we managed to pull together the information that we used to build this presentation.